Hello, Math 3 to 11 students. Did you all have a good rest in Lesson 5? Now the intensity is back up as we move into Lesson 6, Congruence Theory, Part 1. In fact, we had been using congruence here and there sporadically ever since we introduced it in Lesson 2, but, this is big but, all those, at least most of those, had been confined to congruence to 0 or not in place of the divisibility. This time we are going to go a lot deeper than that, so let's restart afresh from the starting point all over again, and the starting point is the division algorithm. Given pair of integers a and b where the divisor b is strictly greater than 0, there exists a unique pair of integers q and r which we call the quotient and remainder, such that a is qb plus r, where r is greater than or equal to 0 and strictly less than b. This is called the division algorithm, even though it is not an algorithm in the strict sense. We still use the term division algorithm because we use this theorem, this result, to set up the long division, which is indeed an algorithm. So there's a bit of abuse of terms. In particular, if the remainder r is 0, so that all this part just drops out, then you'd get just a is qb, some integer times b. In this case, we say b divides a, or a is divisible by b. We also use the terms b is a factor of a, and a is a multiple of b. Remember all those. And also these terms. A is called the dividend, b the divisor, q the quotient, and r the remainder. We can express those q and r especially using the div operation and mod operation, which can be written as the rational number a over b along with the floor function or the greatest integer function, like these. But we're going to talk about the floor function in a little bit more detail in the second half of the course, way later in lesson 12 or 13, something like that, so let's not worry about those for the moment. One more comment, just one more comment, and then we are going to move out of this. The division algorithm for negative divisors is somewhat ambiguous. Some people do it this way, to keep r non-negative, but that's not my preference. I prefer it this way. When the divisor is positive, the remainder is positive. When the divisor is negative, then remainder is negative. All the computer algebra systems that I encountered do it this way. Everything. Here I have Wolfram Mathematica program, but Maple, MATLAB, Magma, they all do it this way. This program is semi-randomized, so you can run it over and over again, and you're going to get different results, and soon you're going to see a pattern. Positive divisor, positive remainder, negative divisor, negative remainder. Of course, the remainder can be 0, in which case b divides a. I have no intention reproving it, so that's it, and we are going to move out of this division algorithm business. And using that, let's define the congruence. Given positive integer m, we say the integers a and b are congruent modulo m, or equivalent modulo m, if m divides a minus b. In other words, a minus b is some integer times m. We can use this notation with triple bar and parenthesis open modulo m, or we can use a second expression, triple bar subscript n. Both expressions are widely accepted, so I'm going to mix those up in this notebook so that you can be exposed to both. Even worse, I'm going to use just triple bar without any specification when there's no danger of confusion. For example, in a single problem, if I'm using just mod 7 operation all the time, then I'll specify once, and after that, just this only. But in a single problem, if I have to use mod 7 and mod 9 and mod 15 all mixed up, In that case, each time I have to specify accordingly. A pair of integers a and b are congruent modulo m if and only if a and b share the same remainder when divided by m. So basically, this congruence creates an equivalence classes, basically, based upon the same remainders. How many classes? Well, the integers 0, 1, 2, 3 up to m minus 1 will become the remainders, right? So there are m such classes. The proof is actually pretty simple, and use a division algorithm here. A is q1n plus r, b is q2n plus r, same remainder, and then just flip this r to the other side. Subtract r from both left hand side and right hand side, and I'm gonna get this, and here I'll drop those, and what do you get? Well, that's precisely the same as a and r are congruent. You see? That's the definition. Left hand side minus right hand side is divisible by m, some integer times m. I can do the same thing to the second equality as well. That's the proof. Let's go back to where it was. Now, in a special case, when the remainder is 0, you can see that m divides a, and a is congruent to 0 modulo m are equivalent. They mean the same thing. Oh, the proofs are left to the students, but I already did it. Let's see, is this worth talking about? Well, okay, let's spend just a little bit of class time. R is a mod m, that means R is the remainder when I divide a by m. And that versus a and r share the same remainder. They mean the same thing when r is indeed a remainder between 0 and m. So that's how the mod operation and modular equivalence are related to each other. But if I drop this condition, then we no longer have the equivalence. We only have one implication. The equality is stronger than equivalence. R is the remainder, so that's between 0 and m. But here, R does not have to be. A and R share the same remainder, which can be something else, say S. That will be between 0 and m. So the latter is a bit weaker. That's how they are related in general. That's a congruence, and that was the definition. And we went through some properties here. Congruence if and only if two integers share the same remainder. Now let's expand that idea just a little bit. Same remainder, what do you mean by that? Well, the best way to describe that is to set up and prove the equivalence property of the congruence. The congruence is actually an equivalence relation. It satisfies the reflexivity, symmetry, and the transitivity. Any integer a is congruent to itself. If a is congruent to b, then b is congruent to a. If a is congruent to b and b is congruent to c, then a is congruent to c. How do you prove those? Well, from the definition, what's the definition of the congruence? Left hand side minus right hand side is divisible by m, some integer times m. That's the way we can set up. So we have to prove left hand side minus right hand side. A minus a is some integer times m. What is that integer? That should be simple. Next, a minus b, left hand side minus right hand side is some integer times m. Then here, again, left minus right. B minus a should be some integer times m. So if this integer is, say, q, what is this integer? Finally, the transitivity. Left minus right. A minus b is some integer times m, and b minus c is some integer times m. Then left minus right again. A minus c is some integer times m. That's what you have to prove. Now remember, in the definition, m is a factor of a minus b. So m divides this, so m times some integer. This some integer is associated to an existential quantifier. See that? Whenever you have an existential quantifier in the proof, you have to bring in a new character. So especially in the transitivity, it's very important that you have two different integers, not the same integer, q1m, q2m. So each time you have existential quantifier, use different character. Please remember that. I've seen too many mistakes all over. Let's go back to the easiest one. What is this integer? Clearly that's 0. So 0 times m is 0. Okay, that qualifies everything. Such integer existed. So this is true. So reflexivity is done. Next, the symmetry. If such an integer exists, let's name it, say, q for quotient, then the second integer is negative q, obviously. I can use different character, doesn't matter, km, negative km, im, negative im. But whenever you have existential quantifier, bring something in, and this one does not have to be the same. Okay, that was a bit harder, but still okay. Now this one is the most challenging. Still not too bad, but to a certain degree it is challenging because whenever you deal with an existential quantifier, you have to bring in different characters. q1m, q2m, all right. And how would you write a minus c? Well, a minus c can be rewritten as a minus b plus b minus c. Subtract and add the same thing, we get net 0. If I do that, then these two can be written as q1m and then this difference can be written as q2m. So what do you get? Factor m out and we get an integer. Isn't that what we want to prove all along? A minus c is some integer times m. There goes the whole proof. The key technique here is to do this. This is what I wrote. As a consequence, we have the transitivity as well. So the congruence is an equivalence relation, and if you know the general theory of equivalence, then you will remember the equivalence classes and quotient set. And you can define a quotient set, and in that quotient set, you can endow an algebraic structure inherited from the original, induced is proper term, induced from the original set, which is Z, and we can prove those are the induced operations are well defined and so on. And that's the way we do it in abstract algebra. But we don't do it like that in 3000 level. I mean, there is some difference between 3000 and 4000. We're going to do it in much easier way in 1.3. Less powerful but easier. But that's something we're going to do in the next video. Let's stop here and see you again soon.